presentation is from Arista, Telemetry in VOQ chassis by Milind and Pandurangan RS. Yeah.
Hello, can you hear me? Yeah. Thank you. All right, so I'm Milind here. I'm from Arista Networks. I have Pandurangan, I have Vishal, Vijay, a lot of big team coming from Arista here. And thanks to the SONiC forum and all the organizers. Thanks a lot for that. Very nice to see some familiar faces from last year and new faces this year as well. Much more crowd than last year actually. Good to see that. We are going to talk about telemetry primarily in the VOQ based architecture. The outline is going to be like this. We'll talk about modular chassis, how the architecture is for the VOQ based modular chassis. We'll talk about SONiC in the again chassis based architecture. We'll talk about distributed forwarding, distributed state. Primary focus is going to be on telemetry, and then more details about telemetry which Pandurangan will talk about. So obvious comparison between any modular chassis versus fixed systems. Obvious advantages are there basically. Much more power consumption, it's only one box that you have to take care of in terms of provisioning, maintenance, everything. Much lesser devices actually to be taken care of, and obviously mean time between failures is much more lesser. And of course the cabling, etc., all that thing significantly comes down when you have modular chassis. Of course, it has its own challenges also to take care of. In specifically VOQ and non-VOQ architecture kind of deployment or the chassis, we will talk specifically about the VOQ based architecture here. Actually, VOQ is virtual output queuing. So this gives much more power in terms of buffering. Why? Because normally any non-VOQ architecture that you might have seen, the buffering for the packets is done on the egress side, the exit side actually. So it's one funnel from all the ingress that comes there, and that could be a choking point. The VOQ architecture gives you a facility of distributing that across the different ingress or input devices. So forwarding resolution on the ingresses, since there are two parts on the left side of your screen is basically the VOQ where packets could be coming in, that's the ingress side. Then multiple of the ingress devices and the egress devices will be connected using something called as fabric, which is much more powerful entity. And on the egress side you will have the basically egress device through which the packet is going out. Majority of the forwarding decisions, majority of the buffering in the VOQ architecture happens on the ingress side. And ingress side pretty much ends up giving reasonable instructions to the egress side to take care of actually what to do with the packet and send it out. But the major intelligence and the forwarding resolution happens on the ingress side. Packets are enqueued on the ingress ASIC in the virtual output queue, as I said. Now that you are on the left side, buffering happening on the ingress devices, you can do much more buffering because it's not now only on the egress side, you are buffering on each and every ingress device. So you get much more deeper buffering with the VOQ architecture. VOQ is connected to destination port anywhere on the chassis. End-to-end credit based system. So now, as you can imagine, it is kind of a pull model. So the egress side actually can tell the ingress side when to send the packet to the egress through the fabric, right? It's not that ingress is just shooting the packet and going to the egress side, and egress doesn't have control. So if you have some shaping applied on the egress side, if you want to do some control, congestion is being experienced, then the egress side, the output side can actually flow control or control the ingress side, and it decides when to pull in the packets. Biggest advantage I would say. Obviously it gives much more deeper buffers to absorb significant bursts. So as you can imagine, among the three devices on the left side, if all of them are pumping traffic simultaneously and together to the egress device can control it. But buffering being separately on the three different devices, you can do much more buffering better, and accordingly the bursts that are coming from the ingress side can be absorbed better. The FE is a fabric element which is sitting in the center, the green box, and that is extremely powerful, extremely I would say efficient piece of the entire architecture. and that pretty much gives you non-blocking forwarding architecture. What it does basically is you can have multiple fabric elements to which the ingress devices are connected, egress devices are connected. And the ingress devices, instead of sending the entire packet through one fabric, it breaks the packets into multiple cells and sprays across the cells through the fabric links, right? What does that mean? Even if one fabric goes down, the entire system can still run almost at the full rate, the full bandwidth that it has. How does this map to SONiC? SONiC basically architecture for the VOQ best things or the modular system is that you will have one supervisor that is controlling the entire system, and you will have one SONiC instance on every line card, right? So every line card will have a processor and you will run the SONiC instance. From the SONiC perspective on the line card, there is nothing else that exists. It's as good as one fixed system that SONiC is running on. Multiple such SONiC instances called as FSI, the forwarding device or forwarding corresponding SONiC instance, and each instance will control all the ASICs on the corresponding line card. So individual FSI is in its own world. It is as good as from its perspective, most of the system is just the fixed system that you can imagine. And as we talked in the previous slide, there are fabric elements. So there are fabric cards also, but you don't need to in the current architecture, we don't really run any SONiC on the fabric card. The fabric card corresponding information is completely controlled and kept in the supervisor, as you can see here. It works great. So as you can see here, these are the two different instances of the fabric card, 1 and the 2, and that is sitting on the SSI, which is the supervisor SONiC instance. So line cards will have their own SONiC instance, but fabric corresponding information is kept directly in the SONiC instance of the supervisor, right? On the SSI, you have a central orchestrator of the entire system, as you can see. Hosts new switch chassis app DB where all the information is kept, as you can see again here. This is the chassis app DB where all the information is collected from each and every FSI or the line card, and the information is kept in the chassis DB. On the FSI, as I said, it runs on the line card and it behaves as if it's working on the fixed system pretty much. It supports single ASIC, multiple ASICs, hosts externally reachable through management IP address. So as you can imagine, the connection between SSI and the FSI is going to be through internal IP fabric that is going to be there. And each FSI being SONiC instance by itself, it has got its own internal IP address through which supervisor and line cards can talk to each other. A simple example of how the distributed forwarding happens. Say there is a packet coming with the MACD R1 and the destination IP address of 10.0.0.3. Basically, that will get looked up in the routing table. Routing table assume that it is going into the two ACMP paths, two at 20.0.0.1, 30.0.0.1, and one gets picked up. And the next hop entry, basically, this is all ingress, as you can imagine. Everything is all the resolution that we talked about happens on the ingress. The destination interface through which the packet is going to go out is also determined on the ingress, which is shown here as 1, 2, 3, 4. And there is some additional information, as you can see here, neighbor index 100, which is basically nothing but the information going to the egress side to take some more or derive some more information from there. So from there, the packet will be created, some additional metadata will be added here, such as, okay, destination port is 1, 2, 3, 4, and the neighboring index is 100, and the remaining packet will go through the fabric. As you can see, we talked about cellifying the corresponding packet, breaking it, sending it to the egress side, and based on the information index 100, more data will be derived from the egress side. As you can imagine, obviously, it's routing example. The destination address needs to be overwritten. That is the R2 here, that will be determined based on the index 100, and the packet will be modified, rewrite, things will happen on the egress, and packet will go out of the box actually. That's typical distributed forwarding architecture that happens in the modular chassis. Again, we are talking about VOQs. Again, a quick example here that if there are multiple ports on the left side through different line cards or different ASICs, sending packet to the one ASIC outside here, the ET3, 4, 5 and the different ASICs are going to be enqueuing packets for the destination interface. Every destination interface, imagine, will have 8 VOQs on every ASIC that it is going to host. So every ASIC has VOQs for every interface in the entire system, including its own interfaces as well. So with that, The packets are going to be enqueued. For example, here just VOQ 0 is shown here, but it can be from 0 to 7. Packets will be enqueued. Now, as you can imagine here, the buffering is happening individually on the ingress side. That is the most important part of it. And the egress side can really keep pulling the data as it needs based on the congestion, based on the shaping scheduling, and the packets will be flowing from ingress to the egress side. Right? That is a typical VOQ based architecture. Now, we will talk more about telemetry. Pandurangan will do that. This is more about deep diving into telemetry, taking one example called as VOQ counters, how those will be transmitted through the telemetry to the collector. Pandurangan will talk about that more. Thank you.
Thank you, Milind. Yeah. So, we will dive into telemetry right away. So, network telemetry refers to the collection and transmission of data to different entities for offline processing analysis. It is very crucial to understand the data which is flowing into the network and also within the node to really kind of optimize it. Yeah, there is no need to emphasize on that. I think probably all of us know here how important it is to really have that kind of visibility into the network. So, SONiC supports modern day telemetry using gRPC and GNMI. Just a quick overview on the SONiC telemetry architecture. So, we will have the telemetry data collector subscribing or getting the data via GNMI get or GNMI subscribe, which is processed by the gRPC server, GNMI server running within the SONiC, within the telemetry container or the GNMI container. Yeah, that is the process responsible in SONiC for handling the request. And then it talks to the DB client, which in turn pretty much can stream out or provide any data access from the SONiC Redis database via the GNMI gRPC framework. We will also cover a bit of what is the virtual DB path, which is there seen in this slide here. Sorry. Yeah, so that a bit later. Okay. So, regarding the VOQ counters per ASIC. So, I think Milind briefly touched upon how the VOQ counters or VOQ is present per ASIC itself, like basically VOQ is there for every interface, every ASIC has the VOQ for every other interface on the entire system. That is the like crucial point to note here. So, as we can see in the example here, for example, this is the its own Ethernet 0 interface actually on ASIC 0, and this is the Ethernet interface, this is the Ethernet 0 of the other person, which is here kind of on the ASIC instance 0. So, and then this is the Ethernet 0 interface of the other one, which is here. So, and there are different queues, basically Q0, Q1. So, this is all stored in the counters DB in the SONiC ASIC instance corresponding when we say ASIC instance, the corresponding Redis instance actually. So, that is having all this data stored, and of course, this data is getting populated by syncd. So, we will be seeing more details later as well. Okay, so just a quick look on pulling the data from Redis database from the SONiC. So, this is about for example, this is the data which is when we say SSI 5, it is the line card 5 actually. So, here we can see that we have interface for its own thing, which is here like Ethernet 0 like we saw, but it also has data counter data stored for other line card ASICs also, or different ASIC, we can say remote ASIC when compare as from this perspective. And the data is not directly available, kind of we can see first there is a kind of counters VOQ name map. So, which kind of maps from the interface name and queue name to something internally called as OID, object identifier. So, it is just some hierarchical data arrangement within Redis database for storing things better, and then we can see, then we can dump the data using that object ID, which is here. So, the same object ID is being kind of dumped here, and then we get into the actual counters, which is So, the different interesting counters are like dropped packets and bytes, and the other one is the forwarded packets and bytes, and this is the watchdog deleted packets. So, this is a special case generally with respect to VOQ architecture, where if the packet gets sitting in the VOQ for a very long time, like some timer is there. So, after that it is completely stored, it is not able to egress out, then it gets deleted simply. So, coming to the existing CLI, yeah, we have an already these VOQ support counters are already supported in SONiC today. So, we can just use that CLI to see the VOQ counters per ASIC. So, this is already there. So, nothing is like new here as such, we are just showing what is already available. We can see that for the remote interface VOQ 0, these are the values. Similarly, for its own chip interface, there are counters again recorded again for different queues, from 0 to 7. So, how does VOQ counters work on FSI? Basically, this is more like how it works on a fixed system before we get into the things of modular system. So, basically there is a flux counter pole which is happening from the SYNCD container actually. So, which kind of makes the corresponding SOI call, gets the counter value from the ASIC and then pushes into the counter DB of the corresponding Redis instance. So, that is how it works, and then we have the CLI obviously which we just saw. So, pulling the data from the Redis and displaying it, and the telemetry support is currently present only for the egress counters, queue counters, not for the VOQ counters. So, that is a new addition. So, we will have a bit more detail on that in the next slide. So, now what about VOQ counters on SSI? So, the basics still pretty much remain the same, just that these arrows in blue are the newer parts that have been built to support these. So, the first change starts from there is a new subscriber which has been created in the arc agent, VOQ stats arc I think is the name. So, which is kind of pulling all these subscribing to the counter DB updates which is happening in the Redis database, and then pushing on the same updates towards the chassis counter DB. Again, this has been newly created on the SSI. So, all the data is getting pushed from here into the chassis counter DB. So, that is the the primary change that has been made. So, in addition to that, for telemetry support we have added VOQ counter support both on FSI as well as on SSI, and also there are some CLI changes. So, that if you run the CLI on the SSI, we will now get the aggregated counters which we will be covering in detail. So, how does the aggregation, or what do we need to exactly aggregate? So, this is like we just saw the ASIC instance, the SYNCD is pushing the data into the counters DB VOQ. So, this is all but let us concentrate on the format of what it is a bit more. So, this is the Redis database on the SSI. So, this uniquely identifies the output interface actually, the prefix part before that. So, this is for that output queue. So, that is the prefix part, and after that part it identifies, it represents the data which is present on a specific ASIC. For example, in FSI 0 ASIC 0, it means it is the line card 0 1 or something, and then the first ASIC within that. So, this is the VOQ counter corresponding for that. The same will be present across different things. For example, if you see the prefix part is now exactly the same. So, the output, this packet is destined to kind of go out on the same egress interface, but it is sitting in a different chip now, the ingress chip is different. So, that is what this part signifies. So, the 3 the first 3, these are aggregated together, and that is put as the output counter for this corresponding VOQ. So, of course, we are talking only Q0 all the time, to keep things a bit manageable on the slides. So, there are other queues as well, typically we have 8 queues or something. Okay. So, just to show a quick example of with the changes how things look like. So, the first 2 parts are pretty much the same, there is nothing new in here, this is already existing. If you run the existing CLI on line card 4 and line card 5 kind of, you just get the, and we specify the corresponding ASIC from which the data needs to be dumped. So, we get the VOQ counters, this is what already we kind of saw, and now this is the new part SSI aggregated counters, where we do not specify any ASIC or anything, and this command has to be run on the SSI itself, not on the FSI instance. So, that is kind of the difference, and we run it, now the data gets aggregated like how we saw in the previous slide. Basically it gets aggregated, and then it just gets displayed as aggregate count. So, basically this will be the sum. So, basically if you see, right. So, this first row and this first row here, that is get summed up here kind of, yeah. So, now coming to how, okay. So, this is why the CLI is all good and fine, but what about, yeah, getting something like through GNMI or something, which is probably more interesting use case. So, let us see how we can try to get this data via GNMI, because anyway the native Redis DB streaming is also supported on SONiC. So, we can obviously use that to get it, but the same challenge comes as we saw with the SONiC DB CLI, which was trying to directly use the Redis command. So, we are able to get it, yeah, without actual modification to the SONiC through this method. But of course, right, it follows the indirection of OID, which we saw already. So, right, we can give the right path from the database, but it will go through this object ID indirection, and then we will still actually get the data. So, for this, yeah, SONiC comes up with a concept of virtual paths. So, where the telemetry module internally translates it to like a different set of data, which may not be arranged in the same fashion as in the Redis database, and then it returns the data, underlying data for it. So, yeah, we started with implementing a new virtual path for VOQ counters and the ASIC instance itself. So, this is more like a fixed system support for the new virtual path first level. So, yeah, with that, right. So, it is the same thing, just that, yeah, we can just see what is the path look like. So, it is like counters, we give the ASIC name, and this is the output interface identifier, and /VOQ tells it is the /Q or Qs is the name for the egress counters, yeah, /VOQ has been added here instead of /Q. So, that gives us the VOQ. So, we do not need to go through that indirection anymore, we directly get the data. So, that is the. So, now coming to the aggregate counters, yeah, almost the same thing. So, we have extended it, how CLI gave us the aggregate data, we will be able to get the aggregated data via GNMI as well, if we talk to the GNMI instance on the SSI basically. So, that is the underlying condition. The path remains still the same, yeah, kind of trying to keep it a bit more uniform, yeah, we do not really need to worry whether we are talking to an FSI or SSI. So, the path still remains the same, but if you make the same query on an SSI, you end up getting the aggregated data. So, current status, yeah, so the aggregate VOQ counters HLD is the one which is right now like proposed for HLD review in the community. It is coming up in the next couple of weeks or so. So, we have HLD review for it, and then implementation, yeah, we have done major portions of the implementation. So, PRs are in progress, yeah, some more changes, yeah, we are ironing out and doing some more changes on the telemetry front. So, things are a bit in progress still, I would say, but PRs have been published, a bunch of them already, and we are targeting 2024-11 release. So, that is it from my side.
Great. Any questions?
Yeah, I'll pass the mic. Yeah.
Thank you. Okay, I'm Naresh from AV's Networks. My question is right. Minimum it gives you the more buffers. Even if you are using single module, you get more buffers at least. So, why distributed only? Why can't we use it in the fixed structure itself? Or is there some restriction that we are only in the modular?
No. That's not the restriction. The question is, do we have to have modular system for VOQ architecture to work?
Right.
No, that's not compulsory at all. You can have single chip system, but still have VOQs actually. The concept of VOQ is you buffer at the ingress for the egress interface. Now, if it is single chip, it has got two parts, ingress and egress, you still can continue to do buffering on the ingress side in single chip system for all the interfaces on the egress side.
So, do we need to enable it through CLI or it is by default?
Do we label it?
We enable it.
Enable it. The VOQs?
CLI? Yeah.
No, VOQs, I mean without VOQs things are not going to work. So, there is,
okay.
You can fine tune definitely in terms of some buffer capacity or some thresholds to be adjusted, EC and double rate thresholds to be adjusted, or VOQs being mapped to specific transmit queues, all that tuning can be done. But bottom line, you need to have VOQs for packets to be buffered and sent out. So, there is nothing like you now enable VOQ based system, that is not the case. It is VOQ based system. Just that you can fine tune the parameters.
Sure. Thank you.
Any other questions?
Yeah.
Sure.
Yes. Yeah, my name is Gaurav from HCO Networks.
Okay.
So I have actually a couple of questions regarding this. First of all, thanks for sharing the insight of VOQ. So first, we are actually going to talk about this VOQ, network topology architecture, which is kind of a alternate to the CLOS, okay, where it's not a leaf and spine. So first part is about scale. So when we talk about like 2-tier or 3-tier architecture, how scalable it is, okay, for the like end user deployment. And second, the latency part. You mentioned that actually it would be using 2 ASIC, right, ingress and egress. So when you say this architecture would improve the latency in the overall, traffic going from NIC to NIC, from one cluster to another cluster? Yeah, that is my question.
So first and foremost, I did not say latency will be improved. No, that doesn't happen. This is a deep buffering. The primary purpose of the system is, one of the reasons is the deep buffering. And the more you buffer, latency is going to go up. It's very natural. The congestion happens, and instead of dropping packets, the real purpose is not to drop the packets as much as possible. So you buffer them. And naturally, the egress side is going to pull based on the credit system, etc. So there is going to be little more latency than usual. That's going to happen. Your second question, how does it fit into the overall class architecture actually? This is meant for class architecture pretty much. So the VOQ architecture is within the box, and once you are outside the box, how do you connect with the next layer? It depends on that architecture. It doesn't have any direct bearing on the VOQ side of it. VOQ is primarily within the box. You want to make sure that as much as possible buffering happens and packets are not dropped. So these two go hand in hand definitely. Generally, if you look at the architecture of the leaf and spine, the leaves are generally the nodes where you don't need too much buffering. The spine side is the much more powerful, generally modular systems where you need more buffering actually. So of course, there are systems which, as somebody was asking just now, single chip systems, those are also there on the leaf side quite a few times. But the primary reason is for the deep buffering is on the spine side actually.
This will also reduce the number of layers when we put into spine and leaf architecture.
That is correct actually.
Okay.
That is true.
Thank you.
This leaf spine is primarily the 2-layer instead of 3-layer architecture. That's very true. And it is primarily achievable because of the architecture we are talking about.
Okay.
That's
Thank
correct.
you.
Sure.
Thanks a lot.
Thank you so much everyone. Thanks a lot.
I am very happy